Section: Introduction. We, in our research, explore how transformers, a type of model widely used in various tasks like text classification, creating maps, detecting objects, analyzing point clouds, and recognizing audio spectrograms, can be adapted to work not just with data from a single source but also with multimodal data. For instance, CLIP is a model that uses pairs of images and text to significantly improve image recognition tasks. This ability of transformers to work across different types of data, treating them as sequences of tokens, is what we call their universal modeling ability. However, there's a catch. When using data from two different sources, like images and text in CLIP, the data needs to be related or paired. This limitation is widely accepted and hasn't been much challenged. For example, it's hard to imagine how a dataset of purely audio files could help improve image recognition on a dataset like ImageNet, given there's no direct relation between the sounds and the images. In our paper, we challenge this limitation. We propose a way to enhance a transformer's performance on a specific type of data, a modality, using unrelated data from another modality. We suggest that training a transformer on one type of data helps it learn a form of knowledge that can be beneficial when learning from another type of data, even if the two data types seem unrelated. To tackle the challenge of using unrelated data from different modalities, we introduce a framework we call Multimodal Pathway. Instead of directly mixing data from two modalities, we use models trained on each modality separately as proxies. We then create pathways between these models to transfer knowledge from one to the other. We name our specific implementation of this idea the Multimodal Pathway Transformer, M2PT. The key to M2PT is how we connect the models. Even though transformers trained on different types of data might use different methods to prepare their data, tokenizers, the core parts of these models, the transformer blocks, are structurally similar. We link these similar parts across the two models, allowing them to share inputs and combine their outputs. This approach is designed to be efficient, adding minimal extra training costs and no extra costs during the model's use, inference. Our experiments across different types of data, images, videos, point clouds, and audio, show that M2PT consistently improves performance. This success suggests that the knowledge transformers gain from sequence-to-sequence modeling is indeed versatile and can be applied across modalities. This versatility might be due to transformers' ability to process hierarchical representations, learning to recognize patterns at various levels of abstraction. In summary, our contributions are: 1. Introducing the Multimodal Pathway framework to enhance transformers by leveraging models trained on different modalities. 2. Developing an efficient implementation of this framework, cross-modal reparameterization, which doesn't increase the cost of using the model. 3. Providing early evidence that our approach can lead to significant improvements across various types of data, suggesting a promising new direction for research. Section Summary. The section introduces the concept of using transformers for multimodal tasks, such as image-text pairs for superior performance in image recognition, and proposes the Multimodal Pathway Transformer, M2PT, framework to improve a transformer's performance on a certain modality using irrelevant data from another modality. The framework connects two transformers trained on different modalities to exploit modality complementary knowledge, and a reparameterization method, named cross-modal reparameterization, is proposed to implement the pathways with marginal training costs and no inference costs, demonstrating consistent improvements in various modalities. In summary, the section discusses the use of transformers for multimodal tasks, introduces the Multimodal Pathway Transformer, M2PT, framework to improve performance using irrelevant data from another modality, and proposes the cross-modal reparameterization method to implement the pathways with minimal training costs and no inference costs, demonstrating consistent improvements in various modalities. Section: Related work. We've been exploring how to teach computers to understand different types of data, like images, videos, and sounds, without needing to be directly told what everything means. This process is called pre-training, and it's like giving the computer a head start in learning by letting it practice on lots of data. Initially, this practice involved a lot of supervision, where the computer was corrected every step of the way. But more recently, we've shifted towards letting the computer figure things out on its own, a method inspired by how we sometimes learn best by just diving in. One popular way to do this self-learning is by playing a sort of fill-in-the-blank game with data, where the computer tries to guess missing pieces. This approach has been especially successful in helping computers understand images better. Another approach, called contrastive learning, involves comparing different pieces of data to understand what makes them similar or different. As we've gotten better at these methods, we've started to use them not just for images but for other kinds of data too, like 3D models, sounds, and videos. In our work, we've decided to use a method similar to the fill-in-the-blank game because it's simpler and helps us avoid mixing up different types of data, which can happen if they share common labels. But there's more to the story. We're also interested in how computers can learn from multiple types of data at the same time, like both images and text. This is trickier because the data needs to be matched up in a way that makes sense. Most of the time, researchers have relied on data that's already paired up nicely. However, we're venturing into less explored territory by trying to teach computers using data that doesn't match up perfectly. This is a new challenge we're excited to tackle. Another part of our work involves something called reparameterization. Think of it as teaching the computer to build extra tools it might need during its learning process. However, these extra tools can make learning more expensive in terms of the computer's time and energy. We're exploring a simpler way to do this that doesn't require as much extra effort, especially when the computer is trying to understand different types of data together. Now, let's talk about how we're actually building this system. We're designing a special kind of computer brain, called a transformer, tailored to understand specific types of data, whether it's an image, a video, or sound. Each type of data gets its own way of being broken down into pieces the transformer can understand. For images, we chop them up into patches. For videos, we look at frames. For 3D models, we focus on points. And for sounds, we analyze the spectrogram, which is a visual representation of the sound's frequencies over time. Our transformer brain has building blocks that help it pay attention to different parts of the data and make connections between them. We're using a design similar to one that's already been proven to work well for images, ensuring that our approach is fair and can be replicated by others. In summary, we're pushing the boundaries of how computers can learn from different types of data, both separately and together, in a way that's efficient and effective. This is a step towards computers understanding the world in a more holistic way, much like we do. Section Summary. The evolution of unimodal pre-training has shifted from supervised to self-supervised paradigms, with methods like mask reconstruction and BERT gaining traction in visual pre-training. Meanwhile, multimodal pre-training methods have traditionally relied on well-aligned data pairs, but this work explores the understudied use of weakly aligned or unpaired multimodal data for pre-training. The proposed method involves designing a transformer with modality-specific tokenizer, modality-agnostic transformer blocks, and modality-specific head, tailored for different modalities such as images, videos, point clouds, and audio spectrograms, using architectural hyperparameters similar to VitBase for fairness and reproducibility. Section. Cross-modal reparameterization. We're diving into the concept of cross-modal reparameterization, a technique we use in our M2PT model to enhance its performance across different types of data, like images, audio, or video. Imagine you have a model that's really good at understanding pictures, and you want to make it just as good at understanding sounds. Instead of starting from scratch, we take a clever shortcut by borrowing the brainpower from the picture understanding model and applying it to our sound understanding model. Here's how it works. Every model has layers that process input data, like a sound or an image, and produce output data. These layers have parameters, which are like dials that can be tuned to get the best performance. Normally, these parameters are adjusted through training. But with cross-modal reparameterization, we take the tuned parameters from a model trained on one type of data, say, images, and use them to adjust the parameters of a model being trained on another type of data, like audio. We introduce two key concepts here: the cross-modal scale and the cross-modal parameter. After training, we combine these with the original parameters to ensure our model doesn't get bloated with extra parameters, keeping it efficient and easy to use. For the more technical folks, when we talk about layers, especially linear layers, we're referring to the mathematical operations that transform the input data into output data. We simplify this process by using the parameters from another model, trained on a different type of data, and a special scaling factor. This way, we can effectively have a single layer doing the job of two, making the whole process more efficient. After training our model with this technique, we merge the parameters from both models, resulting in a single, efficient model ready for action. This approach allows us to quickly adapt our model to understand different types of data without the need for extensive retraining. In practice, we apply this technique across various datasets to test its effectiveness. For image recognition, we use datasets like ImageNet-1K, MS COCO 2017, and AID-20K. For understanding 3D shapes, we use ShapeNet-Part. For audio recognition, we turn to the AUDIOSET2K dataset, and for video, we experiment with Kinetics 400. We train our models in two ways. One where we start with a model already trained on a similar task, pre-trained setting, and another where we start from scratch setting. This helps us understand how well our technique works both when we have a head start and when we're starting fresh. Finally, we measure our success using various metrics, like top 1 accuracy for image and video datasets, mean intersection over union, MIOU, for segmentation tasks, and average precision for object detection. Our results show that our technique can significantly improve performance across the board, proving that cross-modal reparameterization is not just a cool idea but a practical tool for enhancing model performance across different types of data. Section Summary. The cross-modal reparameterization technique allows us to use the weights of a model trained on one modality in a transformer block for another modality, effectively merging the models and reducing inference costs. This involves reparameterizing the layer with parameters from its counterpart in another modality, and after training, merging the parameters to create an equivalent model with no extra parameters. This approach is used to construct and use an M2PT model, which involves constructing the tokenizer and head according to the target modality, implementing transformer blocks with cross-modal reparameterization, and training the reparameterized cross-modal model like a regular model. Additionally, the experimental details involve obtaining the auxiliary model by self-supervised training on a dataset of the auxiliary modality, initializing the target model with weights pre-trained using self-supervised methods on the target modality, and reporting the performance of M2PT models on various datasets using metrics such as top 1 accuracy, MIOU, and box mask AP to assess performance improvements over baselines. Section: Main Results. We started by exploring how well our models can recognize images. To do this, we set up experiments where we used a model called VIT that had already been trained on ImageNet using a method called ME. We then took this pre-trained VIT and further trained it using additional information from models that had been trained on videos, audio, and 3D point datasets. We named these enhanced models M2PT Video, M2PT Audio, and M2PT Point, respectively. When we compared these models to the original VIT model, we found that M2PT Point performed the best. We then applied M2PT Point to tasks like detecting objects in the COCO dataset and segmenting images in the AID-20K dataset. The results were impressive. Accuracy on ImageNet increased slightly, but the performance on COCO and ADE20K improved significantly. We also tried a different approach where we kept certain parts of the model fixed and only allowed some parts to learn from the new data. Even with these restrictions, we saw a notable improvement in performance, which suggests that the additional data from different sources really does help the model perform better across various tasks. It's worth mentioning that improving upon the ME method is quite challenging, but our results show significant enhancements, more so than some other recent attempts. This is a big deal because it shows the potential of using data from different sources to improve model performance. In another set of experiments, we started from scratch, meaning we didn't use a model pre-trained with MAE. Instead, we trained the VIT model from the beginning using our method. The improvements were even more pronounced in this setting, which indicates that our approach of using auxiliary data is very effective right from the start of the training process. For understanding 3D point clouds, we compared our method to others on the ShapeNet part and PartNet datasets. Our method consistently outperformed the others, showing that it's not just images or videos where our approach is useful, but also in understanding 3D shapes. In the realm of audio recognition, we again started with a model pre-trained on audio data and found that our method improved its accuracy. This was true not just when we started with a pre-trained model but also when we trained a model from scratch. Finally, for video understanding, we focused on a dataset called Kinetics 400. Here, we used a model pre-trained on video data and found that our method improved its ability to understand videos, even outperforming several other advanced methods. This suggests that our approach of leveraging data from different sources can also enhance a model's temporal awareness, which is crucial for understanding videos. In summary, our experiments across different types of data, images, 3D point clouds, audio, and video, show that our method of using auxiliary data from various sources can significantly improve the performance of models across a wide range of tasks. This is a promising direction for future research in machine learning and artificial intelligence. Section summary. The experiments conducted under the pre-trained setting involved initializing target weights with a VIT pre-trained with MAE on ImageNet and auxiliary weights from models pre-trained on video, audio, and point datasets. The best performing model, M2PT point, was transferred to COCO object detection and ADE20K semantic segmentation tasks, resulting in significant improvements in accuracy. Additionally, M2PT consistently improved class MIOU and instance MIOU on ShapeNet part and PartNet datasets, as well as top 1 accuracy on the audio set balanced split, demonstrating its effectiveness across various modalities. Section: Ablation Studies. We conducted a series of experiments to better understand how our model, M2PT, works when it's trained with images and uses point clouds as an additional type of data. Here's what we found. 1. When we tweak every linear layer in the model by applying what we call cross-modal reparameterization, the model performs the best. Inside each part of the model that helps it pay attention to different parts of the data, the transformer block, there are several layers we can adjust. Our tests show that making adjustments to all these layers gives us the best results. 2. We start off the cross-modal scale, a fancy term for a multiplier that helps the model learn from both images and point clouds, at 0 for every layer. If we started off higher, the model doesn't do as well. This tells us that the model works best when it begins learning in a state that's similar to where it ended up after its initial training with just images. 3. It's crucial that the model can adjust the cross-modal scale on its own. If we don't let it do this, the model's performance drops. This suggests that the model needs to figure out by itself how to blend the information from images and point clouds. We also explored how the model can learn useful stuff from the point clouds that it can then apply when working with images. We did this in 2 ways. 1. We looked into whether the model is getting better because it understands the hierarchy of concepts, from simple to complex, across both images and point clouds. We tried messing up the order in which the model learns from the point clouds, and noticed a slight drop in accuracy. This suggests that the model does indeed benefit from understanding these hierarchical concepts, which are common to both types of data. 2. We checked if the improvements were just because the model had more parameters to tweak or was starting off from a better spot. We did this by using point cloud data that wasn't trained as thoroughly and found that the model still did better than the baseline, but not as well as with the fully trained data. This indicates that the quality of what the model learns from the point clouds really does matter. Lastly, we discussed how data size affects the model. Traditionally, it's thought that if you have a lot of data in one modality, Like images, it can help improve models working with a modality that has less data, like point clouds. However, our findings with M2PT challenge this view. We found that even though point clouds have less data compared to images, videos, and audio, they can still significantly improve how the model works with these other types of data. This is a big deal because it suggests a new way of thinking about how we can use data from different modalities to improve model performance, especially in areas where we don't have a lot of data to begin with.